We have 3 more lectures for the remainder of the semester. We're going to try to squeeze in Chapter 9 in those 3 sessions, which means 3 sections per day. A couple of notes about the homework. There is going to be no homework for Chapter 9. And Chapter 5 has been, the deadline has been extended to tomorrow midnight. So I sent out an announcement about that this morning. So away we go with Chapter 9, Counting and Probability. Come on now. Introduction to Probability. Imagine tossing 2 coins and observing whether 0, 1, or 2 heads are obtained. It would be natural to guess that each of these events occurs about 1/3 of the time, but in fact this is not the case. Table 911 shows actual data from obtained from tossing 2 quarters 50 times. And it shows the that doesn't show up on the screen, but shows the numbers of each occurrence. To formalize this analysis and extend it to more complex situations, we introduce the notion of random process, sample space, event, and probability. To say that a process is random means that when it takes place, one outcome from one set of outcomes is sure to occur, but it is impossible to predict with certainty which outcome that will be. For instance, if an ordinary person performs the experiment of tossing an ordinary coin into the air and allowing it to fall flat on the ground, it can be predicted with certainty that the coin will land either heads up or tails up. So the set of outcomes can be denoted as the set of heads and tails, but it is not known for sure whether heads or tails will occur. We restricted this experiment to ordinary people because a skilled magician can toss a coin in a way that appears random but is not, and a physicist equipped with first-rate measuring devices may be able to analyze all the forces on the coin and correctly predict its landing position. Just a few of many examples of random processes or experiments are choosing winners in state lotteries, selecting respondents in public opinion polls, etc. The set of outcomes that can result from a random process or experiment is called a sample space. The sample space is the set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. In the case where an experiment has finitely many outcomes and all outcomes are equally likely to occur, the probability of an event or set of outcomes is just the ratio of the number of outcomes in the event to the total number of outcomes. So, equally likely probability formula. If S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, denoted PE, is the number of outcomes in E and the total number of outcomes in S. Notation. For a finite state A, set A, NA denotes the number of elements in A. With this notation, the equally likely probability formula becomes PE equals NE over NS. So, An ordinary deck of cards contains 52 cards divided into 4 suits. Red suits are diamonds and hearts. Black suits are clubs and spades. Each suit contains 13 cards of the designation ace through 10 and jack, queen, and king. The jack, queen, and king are called face cards. Mathematician Diaconus worked with David Aldous in 1986 and Dave Beyer in 92 and showed that 7 shuffles are needed to thoroughly mix up the cards in an ordinary deck. In 2000, mathematician Trefethen worked with his father, a mechanical engineer, and used a somewhat different definition of thoroughly mixed up to show that 6 shuffles will nearly always suffice. So imagine that the cards in a deck have become, by some method, so thoroughly mixed up that if you spread them out face down and pick one at random, you are as likely to get any one card as any other. What is the sample space of the outcomes? What is the sample space of the outcomes with a... Yeah, the 52 different cards, and that would be the sample space. What is the event that what is the event that the chosen card is a black face card? 6. There would be 6 possibilities. King, queen, or jack of spades or clubs. So 6 possibilities. What is the probability that the chosen card is a black face card? 6 and 52. So the sample space is 52 cards. And outcomes in E for black face card being chosen are jack, queen, king of clubs and jack, queen, king of spades. And then the probability of choosing a black face card is about 11.5%. Counting the elements of a list. Some counting problems are as simple as counting the elements of a list. For instance, how many integers are there from 5 through 12? Well, go along the list of integers from 5 to 12, counting each one. So there's 8. More generally, if m and n are integers and m is less than or equal to n, how many integers are there from m through n? To answer this question, note that n equals m plus n minus m, where n is minus m is greater than or equal to 0. Note also that the element m plus 0 is the first element of the list. The element m plus 1 is the second element, and so on. In general, the element m plus I is the I plus 1 element of the list. And so the number of elements in the list is n minus m plus 1. So the number of elements in a list, if m and n are integers and m is less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. How many 3-digit integers are divisible by 5? So integers from 100 to 999. Now, what is the probability that a randomly chosen 3-digit integer is divisible by 5. So how many 3-digit integers? Well, there's the 100s, the 200s, the 300s, the 400s, 500s, 600s, 700s, 800s, 900s, and there's 20 in each one, so 20 times 9 is 180. Yeah, because you're not counting the first the first 100. So 180, sound right? Okay, what is the probability that a randomly chosen 3-digit integer is divisible by 5? Yeah. Yeah. So that's no. Out of divided by 800 or 900. 999 minus 100 plus 1. All right. So that sound right? Let's see here. Let's see here. We did the math on that. And so there are 180 3-digit integers. And then 180 divided by 900, or 1/5 probability. So analysis of many computer algorithms requires skill at counting the elements of a one-dimensional array. Let A1, A2, etc. to AN be a one-dimensional array where n is a positive integer. Suppose that the array is cut in the middle value m, so that 2 subarrays are formed. How many elements does each subarray have? M or m plus 1, wouldn't it? If n is an odd number, it would be m and m plus 1. If it's even, it would be m and m, right? Yeah. If it's odd and even, you get 2 different answers. So option A, array 1 has the same number of elements as the list of integers from 1 through m. So by theorem 911, it has m or m minus 1 plus 1 elements. Array 2 has the same number of elements as the list of integers from m plus 1 to n. So it would be n minus m, or n minus m plus 1 elements. So if n is even, then each subscript starting with 2 and ending with n can be matched up with an integer from 1 to n divided by 2. So there are n divided by 2 array elements with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is 1/2. Now, if n is odd, the greatest even subscript of the array is n minus 1. So there are as many even subscripts between 1 and n as there are from 2 through n minus 1. Then the reasoning of I can be of 1 can be used to conclude that there are n minus 1/2 array elements in the with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is n minus 1 over 2n. Observe that as n gets larger and larger, this probability gets closer and closer to 1/2. Note that the answers to 1 and 2 can be combined using the floor notation. So, by theorem 462, the number of array elements with even subscripts is the floor of n over 2. So the probability that the randomly chosen element has an even subscript is the floor of n over 2 over n. And that's it for that. Come on now, cooperate. Alright, counting and probability, possibility trees, and the multiplication rule. A tree structure is a useful tool for keeping systematic track of all possibilities and situations in which events happen to occur, or happen in order. The following example shows how to use such a structure to count the number of different outcomes of a tournament. Teams A and B are to play each other repeatedly until one wins 2 games in a row, or a total of 3 games. One way in which this tournament can be played is for A to win the first game, B to win the second game, A to win the third and fourth games. Denote this by writing A, B, A. How many ways can the tournament be played? Assuming that all the ways of playing the tournament are equally likely, what is the probability of that 5 games are needed to determine the tournament winner? Well, do the tree. The possible ways for the tournament to be played are represented by distinct paths from the root, the start here, to a leaf, a terminal point, where A wins, B wins, and the label on each branch point indicates the winner of the game. The notations in parentheses indicate the winner of the tournament. The fact that there are 10 paths from the root of the tree to its leaves shows that there are 10 possible ways for the tournament to be played. And these are the combinations that it can be played in. In 5 cases, A wins, and the other 5, B wins. The least number of games in which must be played to determine the winner is 2. And the most that will be needed to play is 5. Since all the possible ways of playing the tournament listed in Part A are assumed to be equally likely, and the listing shows that 5 games are needed in 4 different cases, the probability that 5 games are needed is 40%. The multiplication rule. Consider the following example. Suppose the computer installation has 4 input-output units and 3 central processing units. Any input-output unit can be paired with any central processing unit. How many ways are there to pair an input-output unit in a central processing unit? To answer this question, imagine pairing the 2 types of units as a 2-step operation. Choose an input, choose a CPU. The possible outcomes of this operation are illustrated in a possibility tree. like so. And pairing objects, the topmost path from root to leaf indicates that input-output IO unit A is paired with CPU X. Next lower branch indicates that IO unit A is paired with CPU Y, and so forth. Thus, the total number of ways to pair the two types of units is the same as the number of branches of the tree, which is 12, which happens to be the multiplication of the two combinations, or the two sets of units. Let's see here, the multiplication rule. If an operation consists of k steps, the first step can be performed in n1 ways. The second step can be performed in n2 ways. The k step can be performed in n sub k ways. Then the entire operation can be performed in n1 times n2 times n3, etc., times nk different ways. A certain pin is required to be a sequence of any 4 symbols chosen from 26 uppercase letters in the Roman alphabet and the 10 digits. How many different pins are possible if repetition of symbols is allowed? Quite a few. 4 symbols. No, not 26. It's It's the 26 plus the 10 digits. No. That would be it. 36 to the power of 4. How many different pins are possible if repetition of symbols is not allowed? Yes, so it would be 36 times 35 times 34 times 33. And what is the probability that a pin does not have a repeated symbol, assuming that all pins are equally likely? I think we're getting into some pretty big numbers. Let's look at what they have to say here. So the 36 choices 4 times is 36 to the power of 4. So that ends up being 1,679,616. You couldn't do that in your head? Anyway, and 4-step, choose the first symbol and the second and third and fourth. 36 ways to choose the first symbol, 35 ways to choose the second, 34 to choose the third, 33 to choose the fourth. And then multiplication rule applied concludes there's 1.4 million different pins with no repeated symbol. So you would subtract, let's see here, for C, 84% of pins would have no repeated symbol. Consider the following nested loop. I equals 1 to 4, j equals 1 to 3, How many times is the inner loop iterated when the algorithm is implemented and run? How many times? What are you multiplying or adding here? Okay, you multiplying or adding? No, it's multiplying. Multiplying. So it'd be 12. The outer loop is iterated 4 times, and during each iteration of the outer loop, there are 3 iterations of the inner loop. So the multiplication rule applies. 4 times 3, and you get 12 times. Permutations. A permutation is a set of objects is an ordering of the objects in a row. For example, the set of elements A, B, and C has 6 permutations. In general, given a set of n objects, how many permutations does the set have? No. That happens to be the case with this one, but what is 2n? It's also 2n times 1, right? N is 3. 3 times 2 times 1. What function is that? We covered it before with the n choose r. Factorial, yeah, n factorial. So imagine the following permutation as a n-step process. Choose an element to write first, choose an element to write second, and choose an element to write nth time. Any element of the set can be chosen in step 1, so there's always n ways to perform the step. Any element except the one chosen in step 1 can be chosen in step 2. So there are n minus 1 ways to perform step 2, etc. In general, the number of ways to perform each successive step is 1 less than the number of ways to perform the preceding step. At the point when the nth element is chosen, there's only 1 element left, so there's only 1 way to perform step n. So by the multiplication rule, you get n factorial. In other words, there are n factorial permutations of a set of n elements. This reasoning is summarized in the following theorem. Formal proof uses a mathematical induction and is left to it as an exercise. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. How many ways can the letters in the word computer be arranged in a row? And is that 8 letters? 8 factorial? So there's no repetition of words, so how many ways can the letters be in the word computer be arranged? If the letter CO must remain next to each other in order as a unit. Yeah, 7 factorial. Yeah. Then you don't repeat. You can't repeat for permutations. What if the letters of the word computer are randomly arranged in a row? What is the probability that the numbers or the letters CO remain next to each other in order as a unit? I'm gonna guess it's 1 over 7 factorial. Maybe. I see somebody back there nodding their head. Is that right? Were you nodding your head? Okay. All 8 letters in the word are distinct, so the number of ways in which you can arrange the letters equals the number of permutations is 8 factorial. CO is treated, if CO is treated as a unit, then there are effectively only 7 objects to be arranged in a row. Hence, there are as many ways to write the letters as there are permutations of 7 elements, namely 7 factorial. And when letters are arranged in a row, oh, it's not 1 over 7 factorial, okay. 1 over 8. When the letters are arranged in a row, total arrangements is 40, 33, 20 at part A, and the number of arrangements with CO is, as a unit, is 50, 40. Thus, the probability is 50, 40 over 40, 30, 20, or 1 over 8, 12.5%. Permutations of selected elements. Given the set A, B, and C, there are 6 ways to select letters from the set and write them in order. Each such ordering of the 2 elements is called a 2 permutation of A, B, and C. An R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n elements is denoted P of nr. If n and r are integers and r is less than or equal to n but greater than or equal to 1, then the number of r permutations of a set of n elements is given by the formula n factorial over n minus r factorial. Evaluate 5 and 2. It's 5 factorial divided by 3 factorial, or 5 times 4, or 20. Right? Sound about right? I'm sorry? 20. Yeah, 5 factorial divided by 3 factorial is just 5 times 4. So the number of 4 permutations and a set of 7 objects would be 840. 7 factorial divided by 7 minus 4 factorial. And the number of 5 permutations of a set of 5 objects is 5 factorial. Uh, uh, That is it for that one. All right. Section 3, counting elements of disjoint sets, the addition rule. In this section, we look at counting problems that can be solved by counting the number of elements in the union of two sets, the difference of two sets, or the intersection of two sets. The basic rule underlying the calculation of the number of elements in a union or difference or intersection is the addition rule. This rule states that the number of elements in a union mutually disjoint finite sets equals the sum of the number of elements in each of the component sets. So, yeah, got the theorem there, 931. Suppose a finite set A equals the union of k distinct mutually disjoint element subsets A1, A2, A3, etc. to A sub k. The total is total number in A is going to be the total number of each of its subsets. How many 3-digit integers? Okay, from 1 to 100 to 99, when 999 conclusive are divisible by 5. We just did that one. What was it? 180? 180? All right. Solution to this problem uses the addition rule. Integers that are divisible by 5 and either in 5 or 0. Thus, the set of all 3-digit integers that are divisible by 5 can be split into two mutually disjoint subsets, A1 and A2, as shown in figure 931. Now there are as many 3-digit integers that end in 0 as there are possible choices for the leftmost digit and middle digits, because the rightmost digit must be 0. So there are 9 choices for the leftmost digit, 1 through 9, and 10 choices for the middle digit, 0 through 9. So n of A1 equals 90. Similar reasoning shows that there are as many 3-digit integers that end in 5 as there are possible choices for the leftmost and middle digits, which are the same for the integers that end in 0. So your total is 180. The difference rule. An important consequence of the addition rule is the fact that if the number of elements in a set A and the number in the subset B of A are both known, then the number of elements that are in A but not in B can be computed as being the number of elements in A minus the number of elements in B. Difference rule holds for the following reason. If B is a subset of A, then the two sets have B. Then the two sets B and A minus B have no elements in common, and B union with A minus B equals A. Hence the addition rule: B plus A minus B, the number of NA minus B equals N of A. Subtracting N of B from both sides gives the equation N of A minus B equals N of A minus N of B. Consider the pin numbers again. There are 1.6 million pins with repetition allowed, and 265,000 pins with no repeated symbol. How many pins contain at least one repeated symbol? Yeah? 1.6 million divided by 200, minus 2.65, or 265,000. And is that a typo? Yeah, okay. 265,000, there was a typo. It should have been 1.4 million with no repeated symbol. That number should have been right here instead of 265,000. But yeah, 265,000 that contain at least one repeated symbol. So 1.6, which is 1.6 million minus 1.4 million ish. Solution 2, because there are 1.6 million pins in all, and 265,000 of these contain at least one repeated symbol. By the equally likely probability formula, the probability that a randomly chosen pin contains a repeated symbol is about 15.8%. So probability of S minus A is the probability that the randomly chosen pin has at least one repeated symbol. So when use the difference rule, law of fractions, and the definition of probability in the equally likely case, you get 15.8%. All right, formula for the probability of the complement of an event. If S is a finite sample space and A is an event in S, then the complement of P of A equals 1 minus P of A, where A complement equals S minus A, the complement of A in S. A certain computer access password consists of 3 through 5 uppercase letters chosen from the 26 letters, with repetitions allowed. How many different passwords are possible? How many different passwords have no repeated letter? How many different passwords have at least one repeated letter? And what is the probability that a randomly chosen password has at least one repeated letter? Well, the first one, if a repetition is allowed, it would be 26 to the 4th, right? On A? Uh, 26 to the 4th power? Yeah. I'm sorry, 5th power. 5 letters. Yeah. And if no repeated letter? 20. No, it'd be yeah, it would be decreasing. It would be 26 times 25 times 24 times 23 times 22 times 21 or something. No, factorial would be if it was 26 letters long. So, so the set of all passwords can be partitioned into 3 subsets consisting of passwords with 3, 5, 4, and 5, or 5, as shown here. By the addition rule, the total number of passwords equals the number of length 3 plus the number of length 4 plus the number of length 5. Multiplication rule can be used to compute the number of passwords of each length. Number of passwords would be 26 to the third plus 26 to the fourth plus 25th to 25 plus 5 to the 26th, or 26 to the 5th. Getting tongue-tied here. So the total number is a little over 12 million. Going through the process of 26 times 25 times 24 for no repeated password, no repeated letter in a 3 letter password. And similarly for the 4 and 5 letter passwords. So the total number of passwords with no repeated letter is 8,268,000. By part A, the total number of passwords is 12.3 million. By part B, 8.2 million of these passwords do not have a repeated letter. Thus, by the difference rule, the number of passwords with at least one repeated letter is 4.808 million. Given the assumption that all passwords are equally likely, the equally likely probability formula can be used. So the probability that a randomly chosen password has at least one repeated letter is about 33.1%. Inclusion-exclusion rule. The addition rule says how many elements are in a union of sets if the sets are mutually disjoint. Now consider the question of how to determine the number of elements in a union of sets when some of the sets overlap. Look at the Venn diagram here, and you can see an example of that, where A intersect B is not the empty set. So the inclusion-exclusion rule for 2 or 3 sets is n of A union B equals n of A plus n of B minus n of A intersect B. And likewise, the 3-set version here. How many integers from 1 through 1,000 are multiples of 3 or multiples of 5? Now, how many integers are from 1 through 1,000 are neither multiples of 3 nor multiples of 5? Well, set of all integers from 1 to 1,000 that are multiples of 5 or 3, and B be the set of integers that are multiples of 5. So A union B is the set of all integers from 1 through 1,000 that are multiples of 3 or 5. A intersect B is the set of all integers from 1 through 1,000 that are multiples of both 3 and 5. I guess C would be the set of all integers from 1 through 1,000 that are multiples of 15. Or no, that's a union of, no, that's the intersection of of A and B. So because every integer from 3 through 999 is a multiple of 3, every third integer, it can be represented in the form of 3k for some integer 1 through 133, for 3k for some integer k from 1 through 333. Oops. There are 333 multiples of 3. So n of A equals 333. Similarly, each multiple of 5 from 1 through 1,000 has 5k for some integer k through from 1 to 200. Thus, there are 200 multiples of 5 from 1 through 1,000. And NB equals 200. Finally, each multiple of 15 from 1 through 1,000 has the formula of 15k for some integer k, 1 through 66. Hence, there are 66 multiples of 15 from 1 through 1,000. And n of A intersect B equals 66. It follows by the inclusion-exclusion rule that the union of A and B would then equal to 467 that are multiples of both 3 and 5. Or 3 or 5. B, there are 1,000 integers from 1 to 1,000. 467 of these are multiples of 3 or 5. Thus, the difference rule, there are 533 that are neither multiples of 3 nor multiples of 5. And that would be it for the slides for the day. Trying to go through things quickly. Like I said, you just got 2 more lecture sessions left, 6 more sections of Chapter 9 left. Like I said, there's not. I took down the homework assignments for Chapter 9, though there will be Chapter 9 questions on the final exam. The final exam will be comprehensive, and I'll have next week. I'll have the date and time if you guys don't know it already. Yeah, just one more week left. Have a good day. See you next week.